So this is the last session of the day. It's session 3 on population protocols. We have 3 great talks. They will all happen remotely, but the talks are really great, so please stay in the room or online. The first speaker is Leszek Gąsieniec. He will talk about efficient assignments of identities in anonymous populations.
Okay, I assume you can hear me and you can see my slides. So
Yes.
Welcome to my presentation. It's unfortunate I'm not in Strasbourg, but you know the situation is not helping at the moment. So probably next time. Anyway, it's a pleasure to have you sort of online and in the audience physically there. So my work is indeed on population protocols. So in particular, we are interested in giving names or IDs to individual agents which are anonymous originally. So this is a joint work with Jesper Jansson from Kyoto University in Japan, Christos Levcopoulos and Andrzej Lingas from Lund University in Sweden. So since this is the first talk in the series, so I basically allowed myself to talk a little bit longer about the definitions of population protocols, probably helping a little bit the speakers so in the second part of the session. So a little bit of motivation, so interactions. So why do we use population protocols? It's just to model interaction large and in particular anonymous populations. So the model itself is inherently sequential, but actually it could be interpreted in such a way that it gives a pretty nice, even reference distributed computing model. So there is no structure in the model. So this is a completely unstructured model. So this is why it's so perfect for the distributed model. And you have some inherent randomization. So basically we consider the model with the random scheduler. And even if it's just a purely mathematical model, very abstract, it's still powerful enough to solve some non-trivial problems. We also see a lot of avenues that this model and results in this model can be applied in related fields like biology, communication, nanorobotics, you name it. So in particular, okay, so what we are dealing with? We have a population of size n. This is a usual size for the population, and basically protocol is a sequence of interactions between pairs of agents. Usually see there's a ordered pair, initiator and responder, with the relevant states SI and SR. And basically when they meet, when they interact, so there may be some result out of that interaction, and we'll call this interaction meaningful if one of these states, at least one of these states changed. And basically all the rules governing such meaningful interactions, so we call, or they create a form, a transition function. So what happens is that initially all agents start in some initial configuration, which is represented by some states from this ground set S on the top. I forgot to mention, let me just grab the basic pointer, that would be easier to deal with everything. Okay, fine. So yeah, so they start in some predefined configuration, and basically through those, through the sequence of interactions, eventually all of them end up in some the final configuration. And basically the initial configuration encodes the input to the problem, and the final configuration encodes, the say output of the problem or the solution to the considered problem. Okay, so the consecutive pairs, as I mentioned, is already of agents chosen for interactions is drawn uniformly at random. And basically the probability of this choice is very small because we have so many pairs. So one particular pair is chosen with really the small probability 1 over n squared, and that causes some problems with population protocols. Okay, we try to deliver our solutions with high probability, which is denoted by pretty close to 1 minus 1 over n to c for some constant c. And we consider usually 2 types of algorithms correctness. Sorry, the Monte Carlo algorithms where the high probability refers to the correctness, and preferably, if we can, a Las Vegas type algorithms where the high probability refers to the expected time. Okay, so what do we know? Some basic tools in population protocols. As I said, this is a computational model, so you need some tools. And one of them is just communication, basic communication, one-to-all sort of, dissemination, or it is called here in this model one-way epidemic, basically flooding. And this operation basically is required to spread, message from one agent available at one agent initially, or maybe even more, to everyone, to every other agent in the population. There's only one transition function, one rule. Like if one meets 0, right? So basically, this one, that message that contains 1 is spread on the other agent, which is not informed yet, right? So basically, the initial configuration is just one agent in state 1, all others are in state 0. The final configuration is that all of them are in state 1. Okay, so that was the very simple example. I'm sure if you work in networks, you've seen, this procedure before. But how do we assess the quality of the solutions? So obviously, we consider space and time complexity as in many other models. So the space complexity is the number of total number of utilized states from this ground set S, and time complexity is the number of interactions. Though more recently, we very often refer to parallel time, which is just time complexity, so the number of interactions divided by n. So if you read the paper, I think we refer to interactions. For this presentation, I adopted the parallel time. So I'll be making reference to the basically parallel time complexity. Okay, so why it's so interesting? It has some parallel to PRAM, and also like in PRAM, the solutions which work in polylogarithmic time are considered to be efficient also in this model. So we say that if we have a solution which has a polylogarithmic time, parallel time, so solution, we consider it as efficient. I mean, there are some particularities or peculiarities related to this one-to-one translation. So basically, that is sequential time divided by n, and this was recently discussed in paper by one of my co-authors, Andrzej Lingas and Alistarh. You can find this paper on arXiv. But in principle, also this parallel time refers to the local time of an agent. If you consider like a long, say, segment of time, so basically in segment of time, more or less everyone is making the same number of interactions or contributes to the same number of interactions, and this is what is considered to be a local time. Okay, so there are some other complexities, especially gaining on popularity is message complexity, but since this talk has nothing to do with it, I'll just simply give it a pass. Okay, so I mentioned this one-way epidemic, so like spreading information from one agent to everyone else, and one can prove that this can be done in logarithmic time. So basically, using n log n interactions, and with a space complexity because we only use states 1 and 0. And this logarithmic time is just basically a core time. Any communication, any sort of full communication has to be done in this logarithmic time. So this is like a reference point to which any other algorithms, for example, the best algorithm that you can get is the one that attracts this logarithmic time. Okay, so what other problems can be solved? Problems also that we will need in this presentation. So, for example, leader election. So in leader election, initially everyone is attributed as a potential leader. And what we want to, so this is initial configuration. The final configuration, we want to be left only with a single leader. So only one agent is in state 1 and every other agent is in state 0, referring to the follower attribute. So this, in this case, the transition function is very simple. It's just, the flipped sort of, order of the pairs. If two ones meet, one of them basically becomes 0 and the agent becomes a follower. But you see, if you look at the computation times, so those protocols are very similar, but one works in logarithmic time because kind of like an expansion, like explodes exponentially, but the other one actually it's kind of decreases, diminishes, depletes the number of ones, and towards the end, in order to eliminate the last sort of one, it takes a lot of time to do it, right? So that's the problem associated with this choice of a specific edge. You have only a limited number of edges from which you can choose from. That process may take a lot of time, right? So obviously it's a very nice algorithm for computing a leader. It always works, but it's a very slow procedure. So can we do it faster? We'll talk about it in a second. Okay, what other tools we can use in population protocols? Like in many other distributed systems, we need to have some synchronization tools. And that was introduced in this seminal paper by Andrzej and Alistarh. that basically showing that if you have a population kind of shepherded by a leader across some sort of, you know, say states representing the hours on the clock. So such a system, as I said, led by a leader and followed by the others, will be sort of periodically visiting, you know, the sort of, you know, say time zero, for example, you know, in logarithmic time. There are some other properties that actually the sector in which all agents belong to is not too big, right? It's just basically smaller than pi. So what it means is that we will never really make the wrong decision in which sort of, you know, moment in time we are. We can, for example, report, you know, odd rounds with zeros, even rounds with ones, and this way we know the time has changed, right? So that's a very convenient, and the protocol is very simple. If leader meets with the follower at the same sort of, you know, point, leader goes forward, and if, you know, it's anyone behind, it's just dragged towards the beginning of the clock. Right. So our algorithms require a leader. And obviously, you know, such a slow computation and log n time is not good enough. But I mean, we already know that we can actually solve it faster, the problem faster in log square time with high probability. This is probably not fast enough for us here in some of our algorithms. So there is another paper basically that solved this problem in logarithmic time. And but unfortunately, this is not with high probability. But since we use a larger number of states, actually, we can use yet another algorithm, which is a very simple one. We just draws some minima from a limited sort of, you know, range. And using this sort of, you know, protocol, we can actually compute leader in a logarithmic time, yeah, with high probability too. Okay, so basically, we'll also need a clock to move between the consecutive stages in our algorithms. So we either use a phase clock or we just simply do counting. As I said earlier, this could be also used to count the rounds in the clock. It's the local time of some agents. Okay, so our protocols are silent, which means that eventually every agent reaches one particular state and remains in it forever. And safe. So basically, we introduce this notion that, you know, when you get the label, you never change the label, right? So you just adopt it, and that's it. And we also consider pool protocols. This is somehow what makes our protocol safe. And in this way, basically, at any time, those agents, they're still able to label. They possess some number of labels, and these labels are separate for every sort of agent that can still label other agents. I mean, that sort of, you know, that sort of, you know, content of whom you can label may change in time, but still is always partitioned between those that have, you know, those labels to be used later. Okay, so as I say, labeling is not really that much different from computation of the size of the network, and it requires a linear number of states. And basically, what we try to really answer in this paper is, okay, but, you know, what's the relationship between the number of states and number of labels? And somehow the answer obviously is probably sort of, you know, obvious that you know, it all depends how much time you have, because if you have plenty of time, if you have, you know, this n squared parallel time, so then a simple procedure does the job. And basically you start with all agents enumerated with ones, and, you know, the only rule is that if if two agents meet with the same sort of number, this means, okay, something needs to be done, so one of them is promoted to the next level or gets the next label. And, you know, after n squared parallel time, all labels are spread across the whole population from 1 to n. Obviously, that n means that this is the size of the network, but also as a half product, we have, you know, the labeling of every single node. Okay, so that's what we are trying to achieve. We try to really see the trade-offs between the number of states, number of labels, and the computation time. Okay, so this is more or less the history before us, and you know, we are probably the closest to. I already mentioned the first results from paper 13, and you know, the other two results, 3 and 4, are probably the closest to us because they use a really fixed range from 1 to n. You cannot have more than n labels, and but you know, those algorithms were introduced for the say different model, so they don't translate directly to what we do. Though I must say that this third, you know, result this has a lot of in common with our fast procedure that we will look at, you know, very soon. Okay, so this is what was known before. And this is what we introduced. In particular, we can split our upper bounds into 2 groups. So those say efficient algorithms that work, as I said, this is complexity in terms of interactions, but here it will be log n divided by epsilon in terms of parallel time. And the second group is really referring, but there is a price for that. So basically, you have to use a larger range of labels, and you have to use a larger number of states. So then in the second part, we focus on really fixed range of labels from 1 to n. And obviously, then we jump straight away to this higher complexity, as you could see, in this a summary. And basically, but we try to still squeeze, the number of states to as small number as possible. Okay. So basically, the algorithm that this is the principle for every single algorithm. We first try to create a leader, right? And this is done, with the help of all those leader election algorithms. And we also use the phase clock to stop the leader election at some point. And with whatever is selected, we start our labeling procedure. And then what we do is just sort of like an expansion algorithm. We use this kind of tree, but basically a leader which is placed in position 1, so with label 1 on the top of this tree, then gives a label to agent 2, and then it also gives to agent 3. And these are kind of like give 2 labels to the other agents, and then those give 2 labels to another agents. And we keep running this process for long enough, obviously to the depth log n. And so we don't go beyond that. But it's not really the case that we will just enumerate or give labels to every single agent. We'll be still left with some, after n log n interactions or log n parallel time, with some agents which do not have labels. But we can easily observe that after some sort of c times log n time, we are left with only n over 4 agents which do not have labels yet. So basically, we finish the second round, and in the third round, what we do, we just basically do one-to-one connections with those unlabeled agents. And if any agent from here meets with anyone here, just like, for example, this one meets number 6, so it adopts the label 6 plus n. So this way, we will have, in logarithmic time, labeling using labels from the range 1 to 2n. So you can squeeze a bit more sort of, space in terms of states and labels. So you can improve the number of states to 2 plus epsilon n, and to labels to from 1 to 1 plus epsilon n. Just running this second stage, longer, and basically running it for this time. So if epsilon is a constant, you can still get this logarithmic time, parallel time, and in particular, in the third stage, you are left then not with, say, n over 4 agents, which are having no labels, but epsilon times n divided by 4. And basically, thanks to this, we can just use only, those guys with the largest labels computed during, the second stage, right? So basically of labeling. And this time, there will be some missing from there, right? So I take a group of size epsilon times n here. But that many say labels could be missing here because they are in this other group, right? Unlabeled yet. But still, we have 3/4 of that, so the fraction of epsilon times n. So these would easily, so in extra logarithmic time, enumerate those now with labels I plus epsilon times n, right? So basically, this is, but we use only this top bottom, sorry, not top bottom, bottom right corner in this expansion tree. Okay, so the second type of algorithms are used using a different principle. Here we try to squeeze to as little states as possible, and what we show is actually this very interesting procedure. So basically, after we elect a leader, that leader creates 2 dispensers, and basically one dispenser, both dispensers have labels from the range. The first one from 0 to n minus square root of n minus 1, and the other one is from 1 to square root of n. And basically, they together create all labels from 1 to n, right? So basically, this is a cycle here that this first dispenser creates this more significant part, and then basic control goes here. Then this sort of free agent with no label yet now contacts B, and from B gets this second part, And now, in order to complete, the label formation, it now contacts this agent, to say, okay, go with another choice, right? And when we visit every single time A and B, we do appropriate amendments. So in principle, the idea is that you need to go through such a cycle, as many times as you need the label. So this means N. And unfortunately, as I said, this is a very specific pair that you have to really pair. So that may take time, parallel time N. So altogether, this process will be working in an N squared time. Just remove that. Right. So basically, what we said, okay, so that's the very interesting sort of algorithm, but we can still improve on time. And instead of really generating a single pair of dispensers, we can actually generate k pairs of dispensers, also using this kind of expanding tree. And these pairs of dispensers will basically split the whole range into, say, segments of size n over k, and manage those, say, labels in that specific ranges, at the same time in parallel, right? So then basically, since the expansion is quick, it's only the time of running in circles, in many circles, simultaneously. Now, if you plug in k, as it is suggested here, to this specific value, you can show that actually this complexity of this algorithm is n divided by epsilon squared. Okay, so we also have almost matching lower bounds for these sort of algorithms. It probably would take me a longer time to explain why this is the case. They are not exactly the same. And we also use some assumptions, so we cannot do it. While our algorithms are pool algorithms, the lower bounds only hold in this model, for example, the second one, right? So that's why I think we know quite a lot about it. We are almost there, but in principle, as I said, we have quite efficient upper bounds and some associated lower bounds that actually show our algorithms they cannot be really implemented much better than they are at the moment. Okay, that's pretty much it. I think I finished on time. So thanks very much. If you have any questions, please let me know.
So the second speaker is Hiroto Yasumi. I don't know which time zone he's right now, but it's like he's a crazy time of the day. And we talk about computation protocols for graph class identification problems. So please go ahead.
Okay, thank you for introduction. I'm Hiroto Yasumi at Nara Institute of Science and Technology. Today, I'd like to talk about our research, population protocols for graph class identification problems. So our research also deals with population protocol model. This is a model of multiple passively moving agents. In this model, agents are uniform state machines. And when two agents approach, they update their states by interaction. So this is an image of the population protocol model. So when two agents approach, interaction occurs between them, and they update their states. So next, I'll explain the communication graphs of the population protocol model. In the population protocol model, population is represented by a graph like this. So a node represents an agent, and an edge represents a possibility of interaction. So in previous example, I said that when two agents approach and they interact, then they update their states. So in the graph, this behavior means that the interacting agents connected by an edge and interaction occurs on the edge. And then they update their states. So on the other hand, if there is no edge, then the agents cannot interact. So in the population protocol model, the graph structure of the communication graphs affects its computability. So it is essential to understand the graph property of the communication graphs. So in our research, we aim to understand such graph property. So concretely, we focus on graph class identification problems. The problems aim to decide whether a given graph is in the desired class or not. For example, the given graph is a ring or not. So in particular, we consider problems for line graphs, ring graphs, tree graphs, star graphs, k-regular graphs, and bipartite graphs. So this is an example of the ring identification. So in the ring identification protocols, if the given graph is a ring, eventually agent decides that the given graph is a ring. So this largely represents that the agent thinks that the given graph is a ring. And then they maintain the decision. On the other hand, if the given graph is not a ring, agent eventually decides that the given graph is not a ring. And then they maintain the decision. So for the graph class identification protocol problems, there is existing studies for directed graphs. Concretely, there are protocols for directed lines, directed rings, bipartite graphs, directed trees, and directed stars that work with order 1 states. And these protocols are considered on these assumptions. I'll explain these assumptions later. First, I'll explain what is directed on the population protocol model. Directed edges on the population protocol model give direction to an interaction. So on directed edges, when agents interact, then they have distinct roles, initiator and responder. So by these roles, agents can break asymmetry. So for example, when two agents with the same states interact, then they can transition to different states. Next, I'll explain the undirected edges on the population protocol model. So one undirected edge is equal to two opposing directed edges. So when edges interact, then one of the edges is selected. So in our research, we focus on the problems for undirected graphs. So please look at the existing results again. Although these results are for the directed graphs, some of these results can be extended to protocols for undirected graphs. However, these protocols are considered only on these assumptions, and even on these assumptions, tree identification protocol have not been proposed yet. So in our research, we clarify the solvability of the graph class identification for undirected graphs under various assumptions. So this is our results. So I'll explain these results later. First, I'll explain these assumptions. First, I'll explain a fairness assumption. Fairness is an assumption of interaction patterns of agents. So we consider two types of fairness. One is weak fairness. The other is global fairness. To explain fairness, first I explain a configuration. A configuration is a global state of a population. In other words, it is a combination of states of all agents. When two agents interact and states of agents transition, then a configuration also transitions. Now I'll explain fairness. So first I'll explain weak fairness. Weak fairness guarantees that interaction occurs infinitely often between each pair of connected agents. So this is an execution example of under weak fairness. So this one square represents a configuration. For example, this C0 represents a configuration like this. So agents A, B, and C have states X, Y, and Z respectively. And this arrow represents an interaction. So this AB means that A and B interact at this arrow. So since all agents are connected with each other, in this execution, AB, BC, and CA interact infinitely often. Next, I'll explain global fairness. global fairness guarantees that if a configuration C occurs infinitely often, every configuration reachable from C occurs infinitely often. For example, if this configuration C0 occurs infinitely often, then the configuration reachable from this configuration C0 also occurs infinitely often. So in this example, these C1 to C6 are reachable from C0. Then these C1 to C6 also occur infinitely often. Intuitively, the global fairness guarantees that if a configuration can occur infinitely often, then the configuration actually occurs. Next, I'll explain an assumption of initial states. So we consider two types of initial states. First one is designated initial states. So in these settings, all agents have the same initial states. So we need an initialization to use the protocol. On the other hand, with arbitrary initial states, we do not need an initialization. The last one is, lastly, I'll explain an assumption of initial knowledge of the agents. So we consider three types of initial knowledge. First one is knowledge of the number of agents n. For example, if initial knowledge n equal 5 is given, then agents recognize that the exact number of agents is 5. Another is initial knowledge of the upper bound p of the number of agents. So, for example, if the initial knowledge p equal 8 is given, then agents recognize that the exact number of agents is lower or equal to 8. Last one is no initial knowledge. So in these settings, such n or p is not given. Now, please look at our results again. This table shows the space complexity of the graph class identification problems with undirected graphs. So these black letters represent existing works, and this red letter represents our work. So first of all, with arbitrary initial states, we prove that there is no protocol for each graph. Contrary to the results with designated initial states, by assuming global fairness, there are constant space protocols for most graphs. So in this setting, we propose a 3 identification protocol with order 1 states and a k-regular identification protocol with order k log p or order k log n states. So on the other hand, by assuming weak fairness, we prove that there is no protocol for each graph except for star graph. For star graph, we propose a protocol with order n states that work if initial knowledge of n is given. Okay, due to time constraints, I'll just explain one protocol. That is 3 identification protocol with order 1 states that work with designated initial states under global fairness with no initial knowledge. So first, I'll explain the basic strategy of the protocol. Since 3 does not have a cycle, we construct a cycle detection protocol. So by the protocol, if a cycle is detected, agent decides that the given graph is not a tree. On the other hand, if a cycle cannot be detected, agent decides that the given graph is a tree. Please note that initially, all agents think that the given graph is a tree. That is, all agents think that there is no cycle. So from now, I explain the basic strategy of the cycle detection. So the cycle detection is divided into 3 parts. First, agents select 3 tokens, LSE, LL, and LR. These tokens can move freely on the graph by interactions. So for example, when these agents interact, then tokens moves like this. Secondly, LSE token tries to detect a cycle. First, agents place two tokens LL and LR to two adjacent agents like this. So this LTR represents a placed LR token. And this LTL token represents a placed LL token. And then LSE token tries to find a cycle by using these tokens as a single landmark. So agents can distinguish between left and right side of the landmark because the landmark consists of two tokens. So by these properties, agents can detect a cycle. So this figure shows such cycle detection behaviors. So first, LSE token tries to look at LTR token, and then LSE token tries to find LTL token without passing through the landmark. If agents can do such behavior, clearly there is a cycle, and LSE token can recognize that there is a cycle. On the other hand, if there is no cycle, LSE token just passes through the landmark or cannot find the LTL token. So in these cases, LSE token continue to think that there is no cycle. And after detecting the cycle, LSE token conveys its decision to all agents. So this white node represents an agent with 3 decisions. That is, the agent thinks that there is no cycle. And this red node represents an agent with non-3 decision. So this agent thinks that there is a cycle. So after detecting a cycle, LSE tokens think that there is a cycle and conveys its decision to all agents like this. Please note that the decision of LSE token always has a priority. That is, even when LSE token thinks that there is no cycle, this decision is conveyed to all agents. So the important point is that eventually all agents follow the decision of LSE token. From now, I'll explain the details of the protocol. So first, I'll explain the token election part. So initially, all agents have LR tokens. So these are the transition rules of the token election. When two agents with LR tokens interact, then one of them transition to LL token. So by this transition rule, the number of LR tokens continues to decrease. And since tokens can move freely on the graph, by this transition rule, eventually only one LR token remains. And LL and LSE tokens are elected by a similar way. So when two agents with LL tokens interact, then one of them transition to LSE token. And when two agents with LSE tokens interact, then one of them is deleted. So by these transition rules, eventually one LR token, one LL token, and one LSE token are elected. Please recall that agents follow the decision of LSE token like these behaviors. So in the election part, agents can reset this decision of the LSE token. Concretely, when LSE token is deleted by this transition rule, agent resets the decision of LSE token to this 3 decision. So by this behavior, just after this election part, the LSE token thinks that there is no cycle. This implies that if LSE token correctly detects a cycle after this election part, all agents make a correct decision because all agents just follow the decision of the LSE token. Now I'll explain the detecting behavior. First, I'll explain how to place LL and LR tokens. So LL and LR tokens are placed by LSE token. So first, LSE token places LL token. So when an agent with LSE token interacts with an agent with LL token, then LSE token place LL token like this. And then to place LR token next to LL token, LSE token waits LR token. So in this example, LR token eventually move and meet LSE token. So at the time, LSE token can place LR token next to LL token. So after that, LSE token becomes a detection mode. So this DET represents LSE token in the detection mode. So LSE token in the detection mode tries to find LTL token. Please note that LSE token in the detection mode already looked at LR token when LSE token places LR token. So just by finding LTL token, LSE token can recognize that there is a cycle. So this is an example of the cycle detection. So LSE token moves and eventually meet LTL token. And at that time, LSE token can recognize that there is a cycle. So LSE token decides that the given graph is non-tree. And then LSE token conveys its decision to all agents like this. And please note that since we assume global fairness, agents do these cycle detection behaviors everywhere in the graph. So if there is a cycle, agents eventually detect the cycle. Okay. This is all for my presentation. Thank you very much for your kind attention.
Can you hear me well?
Yes, we don't see the screen, but so the last speaker is Joel Rybicki, talking about fast graphical compilation protocols. Please go ahead.
Right, thanks, and hello everyone. Greetings from Vienna. So I'm going to talk about how to solve global coordination problems fast in the population protocol model on graphs. And this is joint work with Dan and Rati. So we've seen many examples of variants of population protocol models today. So I'll now briefly overview what's the variant we are considering in this work. So population protocols model distributed systems consisting of computationally restricted entities that interact in an unpredictable manner. And here we consider computation in structured populations where the structure of the population is given by a graph G. And each node in the graph corresponds to a single agent that is modeled as a finite state automaton. And the computation proceeds asynchronously via pairwise interactions, but only nodes that are connected by an edge in a graph can interact with each other. And this graph will not change over time, but it's static. And we assume that initially all nodes are indistinguishable, that is, there are no unique identifiers. And there's a large body of work studying what problems are solvable in the population protocol model, as we have, for example, seen in the last talk. And in this work, we're aiming to understand how fast global coordination problems can be solved on graphs. And in order to talk about time complexity, we consider a stochastic version of the population protocol. In this model, interactions between nodes are dictated by a stochastic scheduler, and the computation proceeds as follows. First, each node initializes its state according to its local input. Then, in each time step, the scheduler chooses an edge uniformly at random among all the edges in the graph. After this, the nodes connected by this edge exchange information with each other, for example, their current states, and then update their local states. And the protocol or the algorithm defines how these nodes will update their local states, or what are the transition rules. Now, in the next step, a new edge is again sampled, and the nodes connected by this edge will interact and update their local states, and so on. And this process runs forever. The scheduler keeps on selecting edges at random, and the selected nodes interact with each other. Now, in each step, every node will produce some output by mapping its local state to an output value. And we say that the system reaches a stable configuration if the outputs of the nodes do not change, no matter which sequence of interactions the scheduler picks in the future. So we're interested in designing algorithms that always eventually reach a stable configuration where the outputs do not change anymore and are correct. And preferably, the algorithm should also do this fast. Note that we do not assume here that the protocols have to deal with arbitrary initial states. That is, we are not designing self-stabilizing algorithms. So we can actually assume a fixed starting state. And we measure the complexity of an algorithm using two complexity measures. First, time complexity is the expected number of steps until a stable configuration is reached. And parallel time is simply the expected number of steps divided by the total number of nodes in the system. And space complexity is the maximum number of distinct states used by any node, as before. Okay, so this is the basic setup we have. And our main focus is on two classic problems: leader election and computing the majority value. Now, let's recall how these problems are defined. In the majority task, each node is given one of two colors, blue or red, as input. The task is to determine which of the input colors was initially held by the majority of the nodes. So if the majority of the nodes are initially blue, then all nodes should eventually output blue. Conversely, if red was the initial majority opinion, then all nodes should output red eventually. And the requirement for this task is that in a stable configuration, all nodes output the majority value. So this is the majority task. The second problem we consider is leader election. In this problem, there is no input. The task is to select exactly one node as a leader who outputs a special value indicating that it's a leader. All other nodes should output a value denoting that they are followers. And the requirement is that in a stable configuration, exactly one node is selected as a leader, and this node remains the leader no matter what interactions follow. So the leader cannot move around. Okay. All right, so let's talk a bit about what's known about the complexity of these two problems and how our results relate to prior work. So most of the work studying the complexity of leader election and majority has focused on the case when the interaction graph is a clique. In the clique, any pair of distinct nodes are equally likely to interact in any given step. This essentially corresponds to assuming mass action kinetics in a well-mixed system. So you can think of this as putting a bunch of molecules or agents into a test tube and shaking the test tube vigorously so that the molecules bump into each other in a random way. Now, this is a reasonable model for example, molecular computation. In our work, we go beyond the well-mixed setting and instead consider spatially structured systems where the interaction graph is not a clique. Now the situation is quite different as the interaction patterns now depend on the structure of the underlying interaction graph. And this makes the complexity analysis of many protocols much more challenging. All right, so let's now look at what is known about leader election and majority problems in both the well-mixed setting and in the spatially structured setting. The case of leader election in the clique is pretty much settled. Rati and Soloveitchik showed that any constant state protocol must use linear parallel time or quadratically many steps in expectation to solve leader election. However, if you allow the number of states to slowly grow as a function of the total population size n, then it's possible to get much faster algorithms. Now, after a series of improvements, it's now known that in the clique, you can elect a leader using log n many states in only logarithmic expected parallel time. Now, in the case of general graphs, there's actually a very nice 6-state protocol for leader election that runs in polynomial parallel time in any connected graph. What we show as our main contribution is that in regular graphs with high conductance, you can actually stabilize much faster, almost as fast as in the clique. So we show that in regular graphs with high conductance, such as constant degree expander graphs, it is possible to solve leader election using polylogarithmically many states in polylogarithmic parallel time. but our results also extend to non-constant conductance, and the dependence on conductance is at most quadratic. So we show that if a regular graph has good expansion properties, then we get fast and space-efficient protocols for leader election. The story for majority is fairly similar. There's a trade-off between the number of states the protocol uses and the time it takes for the protocol to stabilize. Constant state protocols are again slower, but if you let the number of states depend on the population size, much faster algorithms exist. Now, very recently, Doty and others showed that leader election can be solved in logarithmic parallel time using logarithmically many states, and this is known to be optimal for a large class of protocols. Now, in the case of general graphs, Drayev and Voinovich gave a 4-state protocol that stabilizes in polynomial and many steps. Similar as in the case of leader election, we show that in regular graphs, the majority problem has parallel time and space complexity of at most 1 over conductance squared times polylog n. So again, in graphs with good expansion properties, we obtain efficient algorithms for exact majority. Right. So this was a sort of overview of the results we get. Now I want to briefly talk about how we actually obtain these upper bounds in the spatially structured setting on graphs. Okay, so since dealing with arbitrary graphs is a bit messy and challenging, we instead simulate a nice synchronous click model in the asynchronous population protocol model on graphs. So while we focus on regular graphs here for convenience, we're confident that the basic approach generalizes to non-regular graphs as well. But for today, we just focus on regular graphs. Now, this nice synchronous model we simulate is not exactly the same as the population protocol model in the click, but it's close enough so that we can adapt techniques developed for the population protocol model in the click. So we can transport ideas from the click world to the graphical setting. But what is this nice synchronous click model exactly? We call it the K-token shuffling model, where K is a parameter of the model. This is a small constant, typically 1 or 2. In the following example, the parameter K is set to 2, and N denotes the number of nodes. The computation in this model proceeds as follows. In each synchronous round, every node in parallel generates exactly K tokens based on its current state. So these tokens represent, for example, messages. And since every node generates exactly K tokens, we have a total of N times K tokens created in one round. So in this example, we have 16 tokens. After this, the tokens are shuffled and distributed back to the nodes so that every node gets exactly K tokens. So in other words, we permute the tokens uniformly at random. Finally, each node updates its local state according to its current state and the tokens it receives. So it can look at what is its current state and what kind of tokens it got. And this K-token shuffling model can be simulated in the stochastic population protocol model on graphs. And the K-token model is much easier to work with as it's synchronous and fully connected. So we can design simple algorithms for the K-token shuffling model, the K-token model, and run it in the population protocol model on graphs and avoid all the complexity dealing with the structure of the underlying interaction graph. And how is the simulation done? I'll give you a brief overview. The basic idea is very simple. Nodes generate their tokens in the population protocol model in order to simulate the synchronous token-based protocol. And then we just randomly shuffle these tokens in the graph using a shuffling protocol. And after we've shuffled the tokens for long enough in the graph, we obtain a random permutation of the tokens that is statistically close enough to a random permutation chosen uniformly at random among all possible permutations of the tokens. Now, This shuffling protocol then allows us to simulate a single synchronous round of the K-token shuffling model. And the main challenge is implementing and analyzing this shuffling protocol. The first challenge is to determine how long it takes to shuffle the tokens to get an almost uniform permutation. To do this, we analyze a variant of the so-called interchange process and bound the mixing time of this process using the expansion properties of the underlying interaction graph. So in the classic interchange process, each node holds a single token, but we consider an extension where each node holds exactly k tokens instead of just one. And the analysis is based on analyzing the mixing time of a random walk on the symmetric group. Second, the nodes need to know when to stop shuffling roughly at the same time in order to switch to a new round. For this, we use a distributed phase clock for regular graphs to synchronize the nodes. Now, putting these two ingredients together is somewhat non-trivial, but these are basically the main ingredients. Now, I'll give you a very quick overview of how these two different processes work. So you will probably then figure out how the algorithm itself, or the simulation algorithm itself, works. So let's start with the shuffling process. So in this process, we assume that each node holds exactly k tokens. At every node, we pile these tokens so that they form a stack, so they have an order. And in each time step, we randomly perform one of the following two operations. In the first operation, we sample a node U uniformly at random among all the nodes in the system. Then we look at the stack of tokens held by the node U and move its top token to the bottom of its stack. So in this example, the highlighted node in the top right corner holds two tokens labeled 1 and 2, and it swaps the order of these tokens when applying this rule. So this is the first type of operation that we can apply. The second type of operation is to sample a random edge and swap the tokens of the nodes connected by this edge. So in this example, these two nodes that are selected will swap the tokens 3 and 5. Now, what we can show that at most 1/5 squared times polylog n steps, the distribution of the tokens becomes very close to the uniform distribution if we keep on applying just these two types of operations at random. So this kind of shuffling process will mix fairly fast. And it's fairly easy to design a population protocol that implements this kind of shuffling behavior, assuming we have some access to some random bits in order to randomly decide on which action to take. Okay, now let's take a look at the phase clocks. The phase clock is fairly simple. Each node maintains a local counter, CV, which is initialized to 0. And in each time step, we sample a directed edge uniformly at random. So we assume that we have this initiator-responder distinction. Then we increment the smaller counter by 1. And in case of ties, we can use the orientation of the edge to break symmetries. Now, this corresponds to a graphical load balancing process analyzed by Perez and others. And from their result, it follows that the maximum difference of any two counters remains bounded by log n over phi on regular graphs of conductance phi. So this actually gives us a very simple and nicely behaving phase clock in the case of regular graphs. And these are basically the two key ideas used in our simulation framework to shuffle the tokens and synchronize the nodes. And with these ideas, we can actually simulate protocols that are designed for the synchronous K-token shuffling model and run them in the asynchronous population protocol model on graphs. Okay. So that's how we get upper bounds for majority and leader election on graphs. Our simulation technique is not actually restricted to just these two problems. It's a fairly general framework. Moreover, while our analysis is actually only for regular graphs and assumes that the nodes have access to some random bits as well, it seems quite likely that this general simulation idea can be extended to non-regular graphs as well. The main challenge is to get nicely behaving phase clock in the case of highly irregular graphs. And we also assume that the nodes have access to a single random bit per interaction. Now, again, it seems likely that one can get rid of this assumption by designing a synthetic coin for the case of graphs, but we don't have it yet. But that's actually all I want to talk today, and I'll thank you for your attention. Thank you.